A planet 124 light years away could be home to life.
Space Telescope. A $10 billion project has taken 30 years to reach this moment.
The James Webb Space Telescope has once again demonstrated its revolutionary power in space observation by capturing its first real image of the exoplanet K2-12B. This extraordinary milestone marks a significant leap in humanity's quest to directly observe worlds beyond our solar system. K2-12B, a planet that had previously only been inferred through the dimming of its host star's light during transits, has now been visually confirmed through the piercing infrared gaze of Webb. This direct imaging not only confirms the exoplanet's existence with striking clarity, but also opens an entirely new chapter in how we explore and understand distant worlds. Before we start, smash the like and subscribe buttons for more updates. K2-12B orbits a star that lies hundreds of light years from Earth, discovered initially through data collected by the Kepler Space Telescope during its extended K2 mission. Though its presence had been deduced by the characteristic drop in brightness of its star, its actual appearance, composition, and environment remained elusive until now. The Webb Telescope, utilizing its near-infrared camera NIRCam and mid-infrared instrument MIRI, captured the planet's direct emission and reflected light, cutting through the interference of starlight with the precision that only this next-generation observatory can achieve. The first image reveals a glowing orb, subtly illuminated by the light of its parent star and framed against the backdrop of deep space. The resolution achieved is nothing short of astounding, showing gradations in the atmosphere and even possible cloud formations. The exoplanet appears to be a sub-Neptune or super-Earth in scale, its physical characteristics falling somewhere between those of Earth and Neptune. Unlike previous data-based representations, this real image roots K2-12B firmly in the catalog of planets that can be studied visually, not just spectroscopically or mathematically. Webb's unprecedented capabilities are transforming the scientific methodology for studying exoplanets. For decades, astronomers relied heavily on indirect methods like transit photometry or radial velocity measurements, which could provide orbital information, possible masses, and atmospheric hints. But these methods couldn't show the planet itself. Webb's successful imaging of K2-12B changes this paradigm. It ushers in an era where planets many light years away are no longer theoretical entities described by dips and wobbles, but tangible, visible worlds with discernible features. The implications of this image go far beyond aesthetic or technical achievement. Direct imaging opens a vital path for atmospheric characterization, especially for planets in the habitable zone. With light from K2-12B now directly observed, scientists can dissect its spectrum more precisely than ever before. This enables the identification of molecules in its atmosphere: water vapor, methane, carbon dioxide, and potentially even biosignature gases. The real-time photon collection from the planet itself means researchers are no longer entirely dependent on interpreting filtered starlight. They now have a direct stream of data providing clarity on chemical compositions, temperature gradients, and weather systems. The raw observational power of the James Webb Space Telescope is magnified by the precision of its instruments, which allow astronomers to resolve exoplanets even when they are extraordinarily close to their host stars from our vantage point. K2-12B orbits a relatively faint star, which, in previous generations of telescopes, made it almost impossible to isolate the planet from the stellar glare. Webb's ability to mask the star's light using a coronagraph and to home in on the faint reflected light from the planet exemplifies the telescope's advanced engineering. This success is not only a technological triumph, but a scientific one that validates years of theoretical modeling. What makes this accomplishment even more intriguing is the nature of K2-12B itself. Based on its estimated size and orbit, it is unlikely to be a gas giant like Jupiter, but also unlikely to be fully terrestrial. The image and data collected suggest a thick atmosphere, likely dominated by hydrogen and helium, with indications of heavier molecules closer to the planetary surface or within denser atmospheric bands. The colors captured through infrared imaging imply thermal gradients, perhaps influenced by internal heat or atmospheric dynamics like winds and convection. Webb's instruments can even trace heat patterns across the planet's surface and atmosphere, revealing day-night cycles and storm systems akin to those found on Neptune or even on Earth, albeit under very different conditions. The significance of Webb's image lies not just in its scientific value, but in its emotional and philosophical impact. Seeing another planet, one that humans have never visited and may never physically reach, strikes a deep chord in the collective imagination. It bridges the gap between cold data and cosmic wonder. K2-12B is no longer an abstraction or a point on a graph. It is a visible world, suspended in the blackness of space, glowing with its own reflected and emitted light. It becomes possible to imagine standing on a craft in orbit around this planet, watching the starlight shift across its swirling clouds. The direct imaging of K2-12B also sets the stage for future studies of similar planets. It provides a benchmark for observing sub-Neptune-type exoplanets, which make up a significant portion of the known exoplanet population. These worlds are of particular interest because they inhabit the size range between Earth and Neptune, a category that has no analog in our own solar system. Understanding them helps resolve fundamental questions about planetary formation and evolution. How do these planets retain thick atmospheres? Are they capable of supporting life, either in a conventional sense or in exotic forms? Webb's success with K2-12B may even recalibrate how target selection works for follow-up missions and observational campaigns. Previously, only large, widely separated exoplanets around bright stars were viable candidates for direct imaging. Now, with this breakthrough, it becomes feasible to image smaller, closer-in planets around dimmer stars, greatly expanding the exoplanetary catalog that can be studied in depth. The methods refined here, calibrations, processing techniques, and data interpretation models, will be applied to dozens, if not hundreds, of targets over the coming years. Another profound consequence of this moment is the demonstration of the synergy between space observatories. The discovery of K2-12B was enabled by Kepler's prolific transit data, a survey mission that identified thousands of candidate planets. But it is Webb that brings one of them into visual reality. This collaboration between missions shows the value of layered observation, initial discovery, characterization, and now imaging. It validates the investments made over decades by international space agencies, research institutions, and scientific communities. Each stage in the journey from data point to planetary portrait has required years of innovation, refinement, and cross-disciplinary collaboration. Webb's image of K2-12B also enriches the field of comparative planetology. With a real visual reference, scientists can more effectively compare K2-12B to known planets, drawing analogies and contrasts that help refine planetary models. Is its atmospheric layering more like Uranus, with high-altitude hazes and cold trap regions? Or does it resemble the steaming atmospheres of hot Neptunes? How do its temperatures, rotation rates, and magnetic fields compare to other exoplanets with similar masses? Having an actual image sharpens every question and grounds every theory in observed reality. This event also brings attention to the human capacity for patient, long-term exploration. The Webb Telescope was decades in the making, and every step of its deployment and calibration has been focused on enabling moments like this. Seeing K2-12B not only honors the promise of the telescope itself, but affirms the collaborative spirit of space science. Thousands of engineers, scientists, and technicians contributed to this achievement, their combined effort culminating in a glimpse of a distant world. K2-12B's image adds momentum to the ongoing push toward discovering Earth-like planets and eventually habitable or even inhabited worlds. While K2-12B itself may not be a prime candidate for life, its successful imaging proves the concept that such observations are possible even across immense cosmic distances. It is a step, an enormous, hopeful step, toward one of the deepest goals of astronomy, finding another Earth. The techniques used here will be refined, scaled, and applied to smaller, more Earth-like targets, especially those in the habitable zones of their stars. Every pixel in this image of K2-12B tells a story of light, distance, and complexity. This is a planet bathed in infrared hues, invisible to the naked eye but rendered legible by Webb's instrumentation. Its light traveled for centuries through the void to be caught and focused by a mirror floating 1,000,000 miles from Earth. This encounter of ancient photons and cutting-edge technology results in a scientific artifact of immense value. The image is not just data, it is a glimpse into another solar system, into the very mechanics of planetary birth, evolution, and perhaps one day, habitability. The successful imaging of K2-12B is a beacon for what lies ahead. It signifies a technological threshold crossed and opens a door to thousands of other worlds waiting to be seen. The Webb Telescope, with its ability to peer deep into the cosmos, will undoubtedly bring more such images into view. But this first one holds special weight. It is the first time this specific exoplanet has stepped out of the realm of inference and into the realm of observation. K2-12B now exists not just in equations but in light. As the astronomical community analyzes the initial image in greater detail, more will be uncovered about K2-12B, its atmosphere, its orbit, its potential moons or rings, and perhaps even geological or atmospheric activity. This one image is a beginning, not a conclusion. It sparks new questions and renews old ones. How do these planets form in such proximity to their stars? What drives their atmospheric chemistry? Can they retain liquid water under certain conditions? What would their skies look like from the surface, assuming a solid surface exists? The unveiling of K2-12B through the lens of Webb is a reminder of the vastness of the cosmos and the depth of human curiosity. It is an affirmation that even in an age where information flows constantly, some revelations still possess the power to astound. There will be more images, more planets, more data, but there will only be one first. The moment K2-12B resolved itself out of the void and into view is one that will echo in the annals of exploration, a marker of where the unknown began to become known. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on James Webb's K2-12B image? Expectations for discovery? We want to hear from you. Thank you for watching, and see you next time.